Hi, this is just going to be a video for me to show you guys some E-field visualizations inside of a Magic Tee. What you're seeing on the screen now is an excitation on the difference port of the Magic Tee. So I'm going to start here in a minute just by showing you how I made the visualizations, and then I'll talk a little more in detail about all the different excitations I applied to this Magic Tee, and we can look at all the fields more carefully. The first step in simulating a Magic Tee is modeling one. You can see I'm in FreeCAD, and I have here my Magic Tee model. Let's see if I can remember how to rotate things. Yes, so we have the collinear port, the H port, and the E port. So if I can slide this guy over and bring up pictures. So in the Magic Tee, this is the configuration I have programmed in. Ports 1 and 2 are collinear, 3 is the E port, or the difference port, and 4 is the H arm, or the sum port. So once we have our model, and we've exported it to an STL, we have to run it in OpenEMS. And to do that, I'll look at the code here. So let's take it from the top. So we're looking at a KU band waveguide, WR62. We have the dimensions here. Everything's in millimeters. 15.8 by 7.9 millimeters is our waveguide dimensions. Yeah, and this is the KU band range of frequencies, or it's the range of frequencies for the WR62, which is most of KU band. So then we initialize our simulation. We have in criteria here, so we can either go to 30,000 time steps or negative 40 dB energy in the system. We're using a Gaussian excitation that lets us excite all the frequencies in this range at the same time. And for our boundary conditions, we're using perfectly matched layers on all the boundaries. So if the name didn't give it away, the way OpenEMS works is it uses the finite difference time domain method. And you'll see a little more about that as we go along. So the biggest caveat with OpenEMS is this, the meshing. You have to do it manually, which is quite painful. So I will show you real quick. Let me disable the line smoothing so it'll be nice and clear. And let's not simulate yet. We'll just quit before this part of the script. So now I can show you what OpenEMS is going to see mesh-wise. So the way OpenEMS works is it has a bunch of basically three-dimensional cells that's defined by these grid lines, and each cell has some electromagnetic wave properties associated with it, and it does time domain solving of the propagation of the wave. So we can see a few things here. We can see I've put all my mesh lines along boundaries of the metal air layers, and also importantly the excitation layers. So you can see this is my excitation. I also have some waveguide ports in the various spots, just so you can see them. I'll turn them on. Right, so these are just for measuring the power leaving the Magic Tee. This is for exciting power into it. You can see we're exciting the E arm, or the difference port. Yes, so now, let me cancel that out. We'll undo that. Now we'll put back in the mesh smoothing. This just gives us more cells for a higher fidelity simulation. We have to import our STL model. We have to define the material properties. In this case, I'm using add metal, so just using a perfect electrical conductor properties. We define all our waveguide ports. You can see here I have TE10. That's because the way OpenEMS works doesn't have a convenient way to rotate it. Not all my ports get the convenience of having their long axis on the x-axis because Magic Tee. So we have to be a little creative with our port rotations, unfortunately. But yeah, we have all 4 of our ports here. We generate our simulation files. We show the geometry just to make sure we didn't screw anything up too bad. And we calculate the port parameters and generate S11. Well, in this case, S33 because of we're exciting port 3. Yeah, and then we can run that simulation. So this will show us our finer mesh. So this is what the mesh looks like after the lines have been smoothed. So much denser, much higher fidelity. So once I click out of that, it's going to start running. And while it runs, we can have a look at the S parameters it will generate. So here is our excitation on the H port. This is the one we're simulating now is this one. Our excitation on the E port, or the difference port. So honestly, pretty bad. Pretty bad. I was a little confused when I first saw this until I found out you actually have to match Magic Tees. So I'll go into that a bit in a moment. But you can see we have, I mean, at 16 gigahertz, we have a third of our power being reflected. Here it's a little over a tenth of our power, but we're not getting an even 3 dB split, which is ideally what we like. We get incredible isolation. You know, we're talking negative 58 dB. That's pretty good isolation on that fourth port. And you can see in the H, it's even worse, at least at the lower frequencies. And we have some kind of simulation artifact error going on here. We have gain, which is not something, well, we have gain reflected power, so it's not something you want to see anytime you do a simulation. Meaning something is wrong. It's probably got to do with some interaction of the perfectly matched layers and the frequency in the waveguide and the metal penetrating the perfectly matched layers. I'm not really sure. Okay, you can see our simulation finished in 1 minute 12 seconds, and we get the same result. So that is how OpenEMS simulates. So we have to match our Magic Tee. The question is, how do we do that? So simple Google search turned up 2 methods. One is these inductive irises. So basically we narrow the opening of the waveguide. So that's one possibility. Second possibility is a cylinder and a cone pushing up into the E-arm, the difference port. Now it's very difficult to model a cone in OpenEMS because of the rectangular grid. You have to use a lot of cells to get a smooth approximation. So I opted to use the inductive irises. I have to set up so we can cut it in half and take a look inside. So you can see we've narrowed that opening here, and we've narrowed that opening here. So we'll take a look inside. So any energy incident on these ports has to squeeze through that opening before it can move on. And we can see what that did to the S parameters from the simulations here. So you can see in this case I opted for a little more wideband match, but of course it suffers at its center frequency. We're still only at 15 dB match. Decent, but not the best. Pretty even power split. And on the other port I tuned it a lot sharper. It was mostly just because I was doing guess and check tuning. I did not calculate these matches in any way, shape, or form. So after about 5 or 10 tries, this is what I ended up with. Same here, you know. I chose 15 gigahertz pretty arbitrarily. You know, it's maybe a little better than trying to tune it up here, what with all the weird artifacts we're already getting. So in this case, the match is quite excellent at the center frequency, but it's a pretty narrow band. You know, it's like a couple hundred megahertz wide. This one, I mean, I guess if you, that's at the negative 10 dB. They're actually not that different, honestly. But yeah, that's how I matched it. To generate the visualizations, we need our field dumps. So to get those out of OpenEMS, we simply add these dump boxes. In this case, I dumped the E field, the H field, and the current density. I'm calling it J just for convenience. I tried to export J, which would be property 2. However, it gave me all zeros. So instead, I exported what it calls current density, and we'll see that here in a second. So, you pull that all into Paraview. It's very simple, you know, to pull in the data. You open it, you go into your simulation dumps, you pull in the time series data for each of your field components. So let's start at the E field. So for the E field, I pulled it in, and I added a glyph filter, basically. And that gives us these lovely two-dimensional arrows. Now this is the difference port excitation. So You can see the arms are out of phase. The field's pointing up here, down here. We can see, there we go. You can see the fields rotate as they sort of hit the iris and they fold outwards. You can see there's very little E fields, very little power flowing here. I also, of course, added the STL file just so I have a rough visualization here. Right? Oops, do not want to. Oh crap! I moved something important. Oh, this is a transform. Reset. Okay. Yes, so we can see the visualization. We can see the E field, and we can hit play. So I rendered all these animations externally because some of them play quite slowly. So you can see, maybe right now, the E field energy propagating down to the middle, spreading out between the 2 ports out of phase. So that's the first visualization. The second visualization are H field. I used here a stream tracer. So this is using, oh god, I moved the thing again. There we go, okay. This is using Ranga Kata to trace the field streams. The sphere you're seeing, that is the seed points for the stream traces. That's also why this produces very jittery field lines. It's not tracking the same field line, right? In each time iteration, it has seed points, and it uses Ranga Kata to trace the vector field lines. Oh. You can see we got energy coming in, going off. And you can see we're being pinched in the inductive iris pretty clearly here. Let's see how well this one plays. Maybe get some better insight. Yeah, it's playing pretty slow, but you can see the field's pinching off, pinching apart, squeezing through the iris. Here you can see it narrowing, right? And then energy is getting down inside the MagicTee center, and then it's, can I rotate? You can see it splits apart, and it's half flows this way, half flows that way, and teeny tiny bit leaks out. So that's pretty cool. So we can pause that. And the last one, and my favorite, is the current density. So we can look at our surface current. Now it does seem to also show displacement currents, which is why I have these clipping planes. So if I look to the last clip, you can see we're removing all the currents that are inside the waveguide. And that just makes this a little easier to look at, so we can just focus on the surface currents. Because there would be small displacement currents floating around in the middle of this visualization if it was not for that, that clipping. So yes, we've added glyphs. In this case, oh yes, and you can see OpenEMS calls the current density ROTH. No idea why. Alright, and since this is, of course, the difference port we're exciting, you can see where, it's a little hard to tell. The currents are expanding here, and they're converging here on the mirror point. Right? So, it's a little interesting just how this thing works. I still don't really understand it, but it's cool. But yeah, you can tell they're out of phase because converging one side, diverging the other side. And it's also interesting the singularities where the current is either diverging or converging. That is where there is the least current. Most of the current is between the singularities. I guess that probably makes sense. There are some weird artifacts. I think once again it's got to do with the boundary layer, the fact that the metal is in the boundary layer, the perfectly matched layer, and it causes these strange currents to occur that are not real. They're simulation artifacts. And this one plays the slowest, but we can give it a try. We'll play them all in full speed soon. But yeah, you can see the power coming down the arm and then propagating outwards. And you can see the visualization of the surface current, right? There's these singularities, and you can see the curvature of the fields here. You can see that the direction, you can see it wrapping down. You can see that very, is that right? I think, yeah, it looks like the lines. Let's see what happens, because I'm not sure if I'm looking at this right. Okay, these are vertical. Ah, yeah, we're seeing through a hole. You can see there's actually... am I looking at that? Let me pause it. Okay, yeah, so you can see it quite clearly. all the fields on the edges are very vertical for this mode excitation. And you can actually see there's a gap in the currents here, because that's what we went over in class. So that's pretty cool to see here in the simulation. And you can also see very little power going out this arm. And that's pretty much how all the visualizations were made. So now we can go and take a look at excitation of the various ports in beautiful animated detail. This is the difference port excitation. We can see energy coming in from port 3, the top port, and then it's exiting the collinear ports 1 and 2. It is out of phase in this case. It's a little bit hard to see. I think the easiest place to see it is probably... actually, arguably none of them are... it's going to be the E field because you can see the arrow vectors. But yes, quite beautiful. I just wanted to take a quick moment to look at how exactly all these components are aligned in freeze frame. So you can see here the H field is kind of centered around there. So you can see where the H field is swirling around is also where there's no E field. The edges of the H field are where the E field is intensest. Same here. You can see right there's a lot of E field, H field lines. There's a lot of E field lines perpendicular. And of course the direction of energy propagation is perpendicular to that as well. So right, we got H field going this way. We got E field going this way. We got propagation this way. I unfortunately didn't add arrows to the field lines, so we can't see which way they're actually going. But the other thing is, where are the singularities in the surface current? And you can see there's one right here where there is no E field. And interesting enough, where the E field is the most intense is where the current appears to be the most intense. So yeah, the singularities seem to align with the lowest field strength, and the highest current zones seem to align with the highest field strength. This simulation shows an excitation on the sum port. So we will see that the collinear ports now have in-phase RF power coming out either side. Once again, should be easiest to see in the E field. I thought it would be good to see what would happen if we just excite one of the collinear ports. You can see from the S parameters in the bottom right, it's quite a mess. Interestingly enough, at our match frequency of 14 gigahertz, the E and H arms get an even power split. However, there's still a significant amount of power leaking into the other collinear port. Here we're exciting the two collinear ports in phase, and we expect it to come out the sum port. And what do you know? It does. And you can see on the right, yes, you can see we have very little power leaking into the other port. So it's working quite well in this configuration from the S parameters. Here we're combining power out of phase, so we expect to see a result on the difference port, and we do. Thing to note about the S parameters I'm showing, they're not S parameters. It's just really trying to show the isolation here. So you can see there's a pretty good isolation between the power on the sum versus difference port. I thought we would also have a look at excitations on ports 3 and 4. You can see from the S parameters that the isolation not nearly as effective as on the collinear ports. This is a in-phase excitation. So you can see there's a slightly more power flowing to the first collinear port in this case. With the out-of-phase excitation, you can see that the S parameters are almost exactly opposite, which is interesting. Doesn't necessarily make sense to me. Maybe it should, because the collinear ports are symmetric. Anyway, you can see the power is flowing out port 2 in this case, opposite of the last time. The rest of this video is just going to be the field visualizations with some relaxing music. Enjoy!